because next Tuesday will be the exam on acids and bases and solutions. And then we'll have a review after that. So here's what everything will look like. Today, we're going to continue chapter 10, talk about acid-base strength, and we'll get to a couple other topics. And then Thursday, you will have a quiz on chapter 10. So that'll be live all day. So that'll be your last quiz. This week, we're doing the vinegar titration lab in person. So you'll come to campus, do that, and then complete the Blackboard assignment for your points by Sunday. The chapter 10 homework is up and available, and you have a whole week to get that done. All right. So the lab, the quiz, the homework, that's really it for us. Leading up to this last exam 4, which it's obviously the final is the last exam, but the last 100-point semester exam. I'm going to have what I call a review session Thursday, right after lecture. It is during my typical scheduled office hours, but I'm just going to go ahead and call it a review for exam 4. So if you want to join, I know we will have just finished lecture, so your brain might be like done, but I'm going to record that session and post it as well. And all I'm going to do is work some homework problems. I actually have a homework problem today in lecture that I'm going to work from the chapter 10 stuff. And work other problems from chapter 9 to get us ready for exam 4, do some review. And then next Monday, so we don't have any labs scheduled next week. All right, this week is our last lab. So because we have no lab scheduled next week, I'm going to use all of my time next Monday, 8 a.m. to like noon. I'm going to do 2 review sessions, probably similar to what I did right before exam 3. I'm going to hold an 8:30 to 9:30 review session and like a 10 to 11 or something like that. And then also this week is a little bit of a crazy week for me, so I haven't got it out yet. But before the end of the semester, I'm wanting to get feedback on the Mastering Chemistry homework platform. So I'm going to send a Google form to everybody. I think I told the other section this, and I would love just your feedback on either, I don't know what style questions they may be yet, some open response or some multiple choice, just on how you feel about Mastering Chemistry, if it really isn't that bad overall and it's decent and it helps you study problems, or if you just hate it completely and would not ever want to do it again. I don't know. So different people feel different ways. I know everybody's had maybe hopefully an okay experience to some degree, and you probably had some times where you really don't like it, but I'm going to send that out. And then what else? Reminder that you can do the eval for bonus points. That will go towards, I think I'm going to put it on your exam 4 because I don't have any bonus opportunity for that just yet. So for five bonus points, and you'll get the full 5. Okay. There's no like, oh, I did it, but I only got 2 out of 5 points. If you do the eval, you're going to get 5 bonus points on exam 4, but you have to send me a picture of the completed, like it shows that you did it. Just email that to me. A lot of people have been sending those emails. If I don't respond to you, I did get it. But I just have a lot of them. So I try to say thank you if somebody sent one, but I haven't done that for everybody. So just know that I am getting them. And don't forget to do that. So I think that's it. So we'll do a review next Monday for exam 4. Then we'll have the exam on Tuesday. And then after that, it's just going to be reviewing for the final. Okay. So next Tuesday is exam 4. After that, we do have technically one more scheduled lecture day. It's the Thursday before study day or dead day or whatever you call it. And I'm still going to get on Zoom at our scheduled lecture time, and I'm just going to review. I don't call it an optional day because I want everybody to attend. Obviously, I'm not introducing any new content, but I am going to start with chapter 1, and I'm going to get probably chapters 1 through 4 is how far I usually get on the review. And then the very next day, Friday, which is like your scheduled study day, no class, nothing mandatory, I continue the review, and I do like chapters 5 through 9. I don't really do a review on chapters 10 because we just studied it and you just took an exam on it. Okay, so I really spend time reviewing chapters 1 through 9. And then your final is the time listed is on the syllabus. It will be at the scheduled time for the scheduled amount of time. And you'll get on Blackboard as usual and have that time to complete it. And that'll be it. So any questions from you guys? I know that's a lot. I know you have a lot going on in your other courses as well. So take a deep breath, everyone. You can make it. You can do it. I've enjoyed having you in the course so far, or all semester, and I know you're going to finish well. So any questions from you guys? Okay. Well, without further ado, let's look at acids and bases. Okay. So we finished, oh, you can't, there it is. Sorry, my screen is lagging behind where I actually am. We finished right here last week. I'm going to give a little reminder of what we talked about last week, a little refresher. Yes, you can send me a screenshot of the completed course eval. All right, so last week, what did we do? We talked about what acids and bases are and what they do. We defined them and we looked at how they behave in chemical reactions. So we did this practice problem where we identified which one's the acid, which one's the base. Okay, we did that. Then we introduced conjugates, was really the last topic. And we said every acid and base, when they react on the product side, you get the conjugates. And you can identify conjugate acid-base pairs. All right, so we did that. Let me scroll down. Did some practice problems. And then we finished with this one where we talked about this amphiprotic molecule. Amphiprotic meaning it could give away a hydrogen, act like an acid, or it can receive one like a base. And we drew reactions of that with water, okay? So we're now going to talk about this idea that acids and bases have different strengths, okay? So I'm going to pose a question to you that I think you'll know the answer to. So it might be a silly question, but it gets the point. HCl and vinegar, okay? In fact, this week in lab, we're working with vinegar. Both of them are acids. Vinegar contains acetic acid. So my question is, which one would you be willing to drink? Which one would you be willing to ingest? If you had to take a swig. People do drink like a spoonful of apple cider vinegar. Have y'all heard of this? Supposedly it's like really good for your health. I'm not sure why. I don't do that. But so obviously, yeah, the vinegar, okay? You'd be willing to drink some vinegar if you had to. It probably would not taste good. But that's because, why is that? Well, HCl is highly corrosive. What does that word mean? Anything that's corrosive eats away at something that it touches. Okay, that doesn't sound good. While vinegar is edible. We use it in cooking. We use it in other things, I guess, obviously lab experiments. But why? Why is one safe to ingest while another one's different? Why are they both acids, but we see they have different physical or chemical properties, I should say. Well, it depends on how easily the acid disassociates. Okay, and what I mean by that is how easily it gives up the hydrogen ion, right? So strong acids, I'm gonna continue with my example, HCl and acetic acid. HCl is the strong acid here. It will completely disassociate into what? Well, water is gonna be the base. It's gonna act like a base here. So if water is the base and HCl is the acid, we know HCl is gonna give up its hydrogen, and what we'll have left is Cl minus, once it gives away the hydrogen, and then we're also gonna make H3O plus. You guys remember what we call H3O plus? What do we call it? Hydronium. Thank you, Grant. And I want to make a big deal out of the fact that I'm writing a single directional arrow. Okay, what that means is this reaction is going to go to completion. Okay, and you will end up with all products. That's what strong acids do. They will 100% disassociate. Okay, so if you start with 100 molecules of HCl and 0 of these things, when it's done, you'll have 0 of your reactants. You'll have 100 molecules of these things. Does that make sense? It will go to completion. Single arrow. Weak acids are different. Okay, how are they different? Well, they don't disassociate completely, okay? We say they partially disassociate. I have a question about H3O here. So H2O is the base, so it's going to grab this hydrogen off of HCl. When it does so, it'll become H3O, all right? That's the hydronium ion, all right? Because we've added a hydrogen to it because the base donated, or sorry, the acid donated and the base received it. So that's why you have H3O on the product side. All right, weak acids, we say they partially disassociate. So this is acetic acid, CH3COOH, plus water, which again is the base here because it's in the presence of an acid. Water kind of does whatever, it acts a certain way depending on who it's around. Okay, so if it's around acids, it's going to act like a base. So again, here's our acidic hydrogen. So water is going to receive that hydrogen. What's left from the acid after it gives away a hydrogen is CH3COO, acetate. That's the acetate ion. That's a polyatomic ion. Plus, we know we get H3O plus. Okay. Remember how things change charges? Okay. So we're demonstrating that. But what I want to make a big deal out of here is not the charges and not even necessarily the products we get, but this fact that we have a double arrow. Okay. Because acetic acid will partially disassociate, make some products, but then those products are not really the strongest or weakest acid or base. They're kind of just in the middle, so they can react as well. Remember, the conjugates that you form are weak acids and bases. They can react as well and reform your initial reactants. Okay, so that's why you have a double arrow here. You could get both forward and reverse reactions going. All right. So questions on this. We don't know to what extent necessarily certain weak acids disassociate. They're all different. Some of them disassociate maybe 50%. Some of them disassociate maybe only 20%. So you would have to have some information in the problem if I ask you a question about weak acids that lets you know. But we'll work an example problem in a little bit. Bases though. So if acids have different strengths, bases also have relative strengths. Strong bases have a high affinity for H+, so it binds the H+ really tightly. You could say if you have a weak acid in the presence of a really strong base, it'll drive that reaction to completion. It'll take every acidic hydrogen the acid would give up. Another question in the chat was this. Let me scroll back up. How do you know what hydrogen to get rid of? So we talked about this last week. We said if you have an organic acid where it has carbon in it, the acidic hydrogen is the one that's bonded to like the COOH group. Remember we talked about carboxylic acids? So that's why this hydrogen is the one that's going to be given away. Okay. Grant said, do acids in water always make H3O plus? Yes. It's a great question. They sure do. Okay, going back to bases, strong bases have high affinity for H+, weak bases have low affinity for H+. So let's look at two examples. We also last week said anything with OH-, that's a strong base. So sodium hydroxide, lithium hydroxide, calcium hydroxide, anything with hydroxide is a strong base. So this strong base is water is not really an acid. So this reaction is not driven by water here. It's driven entirely by sodium hydroxide, that the lone pairs on the oxygen will grab a hydrogen off of water. And what do we have left over? So we're going to make, if we have one hydrogen here plus OH here, okay, these are going to make water. So the products are going to feel very redundant here, but this is what happens. And then what's left over from water? When it gives a hydrogen away, you will have the sodium cation, okay, Na+, and then you have OH- left over, all right? And so these, we might write it like this, NaOH, aqueous. So look, your products and your reactants are like the exact same thing. Okay, that feels weird, but that's what happens with a strong base NaOH with water. Okay, when you trade the hydrogen, you just end up getting the same products. All right, a weak base. So ammonia, NH3. This is a weak base. So just like a weak acid, what do you think we're going to draw? We drew a single arrow up on this strong base reaction. Reaction will go to completion. What about a weak base? Well, we're going to get a double arrow. Ammonia doesn't have as high of affinity for hydrogen ions as OH minus does. But it is still, the lone pair on the nitrogen will still grab a hydrogen off of water. And when that happens, we'll get NH4 plus. And what's left over after water gives away a hydrogen is just OH minus. So get a double arrow here. Rachel said, how do we know if it's strong or weak? I'm about to show you a table that lists a whole bunch of, I think that's actually on the next slide. Yep, here it is. So everybody get on this slide. Yep, here's how you know if it's strong or weak. This is not an entirely universal list. So there's other acids and bases, but it's got a lot of them on here. And this is right out of your textbook, okay? Table 10.1. So if you want to go look at the textbook as well, it's in there. But it does show you, so on the left side, the red arrow, this is all the acids. Okay, these are acids. And then it shows you the conjugate base. So everything on with the blue arrow is a base. And what's nice is that it pairs up the acid with the conjugate base. So for example, we just looked at one in the middle, HSO4 minus. When that gives away a hydrogen, what's left over? SO4 with a -2. That's the conjugate base. This is a base, and you can see their relative strengths, okay? Meaning their strength relative to other acids and bases. So the way this is ordered, you can see it says as you travel up the left side of the table, the acid side, you increase in strength. So starting down here at the bottom, we have the weakest. Okay, water is the weakest acid we know, all right? And then as you go up, you have, we say very weak acids, and then these acids in the middle are weak acids, and then these acids at the top are really strong. So there's 6 strong acids. You do not have to memorize them. You will have this table on your resources page for the exam. But it is good to maybe recognize some of them, okay? Like HCl, like H2SO4, or HNO3, and be like, oh yeah, that's a strong acid, okay? I think that will help you on the exam if you take some time and pick out a few. But you can always double check. If you're like, I don't remember if HF, that seems like it would be a strong acid, but it's not, it's a weak acid, okay? All right, and then on the base side, so if it's a really strong acid, when it gives the hydrogen away, all these conjugate bases are the weakest, meaning they really hardly even act like a base. So if it's a strong acid, when it gives the hydrogen away, the conjugate base is super weak. If it's a weak acid, such as water, when it gives the hydrogen away, look what you made. You made the strongest base there is, hydroxide ion, okay? So the trend, there's a trend here, which is kind of nice. All right, I think that's all I'm gonna say about that. Any questions on this table or how to read it? Okay. All right. The next topic we're going to get to, you're going to be excited about this one. Because the dissociation of a weak acid is an equilibrium, meaning there's a double arrow, guess what we can do? We can write an equilibrium equation for that dissociation. All right. I'll let you tell me how you feel about that. I feel like this about it. Okay. Equilibrium expressions. You guys remember equilibrium expressions? That takes us all the way back to exam 3. We learned how to do equilibrium expressions. Some of your faces right now are killing me. We learned how to do equilibrium expressions. Nobody looks happy. Why does nobody look happy right now? We learned how to do equilibrium expressions back in chapter 7. So I'm going to remind you what that is. When you have a reaction such as A makes B, remember we write an equilibrium expression K. And K is equal to the concentration of your products over the concentration of your reactants. Okay, that's equilibrium. And we raise everything to the power of its coefficients. So let's apply the same thinking here to the dissociation of a weak acid, where K, we're just going to write the concentration of the products, which is H3O plus. Everything here has a coefficient of 1, so we don't have to raise it to the power of anything. Oh, I meant to write A minus here, not on the outside of that. Then we're going to divide it by the concentration of HA times the concentration of H2O. Okay, because those are reactants. So that's what you would write, right? Now, there's one modification we're going to make, and here's why. Let me explain it. Okay, there's one modification from just regular old K when we're dealing particularly with an acid. So I want to read through these steps. Even though water is a reactant, okay, here's water, it's a reactant in our equation, it is also the solvent. You guys remember solutions have two parts. So the acid here would be the solute. Water is the solvent. What does that mean? Why do we care? Because of that, the concentration of water is so much bigger than anything else in the reaction, okay? Like there's tons and tons of water because it's a solvent. So if we were to plug it in, it would literally just drive this to an infinitesimally small number every single time, and it would be useless to calculate K, okay? Because this would be such a large number. This would be so big, okay? And when you divide something by a big number, it just drives your answer to 0, and we would get nothing, no information out of K. So because of that, water, concentration of water is not significantly affected when the acid dissociates. It doesn't change by much. And so what we're going to do is we're simply going to pull water out of the equation and recalculate K and see what happens. Okay, so we're going to group water with K and write the acid dissociation as Ka. All right, so when we do that, so here was the original K we wrote right here. We're just going to take water out. Take water out. And when you do that, I'm going to scroll down. You get an equation that looks like this. Ka, we're just going to call this K. We're just going to pull water out of the equation and we just call it Ka. So you're just literally going to write it like this. Ka is now equal to H3O plus times the concentration of A minus. This is your conjugate acid and base over the concentration. HA is your original acid. I'm going to actually scroll back up in just a second. So these are the products. And this is your weak acid, okay? This is if you have any sort of just generalized reaction here where this is the acid. It's a weak acid though. And it's reacting with water. Well, let me write water in. This is what we just saw on the previous slide. And we're making H3O plus and HA. Okay. So for just a general this is just the dissociation reaction for any weak acid. Okay, we're just abbreviating the acid as HA. So we could plug in so many that you could go look at that table. We could plug in any acid for HA right here and rewrite the equation. Okay, and then we could write Ka for that, and you would just plug the formula for your weak acid in right here. Okay, so I have a question though. We have other kinds of acids. Why do we not write Ka for strong acids? Why do we just write it for a weak acid? Anybody? Somebody knows the answer to this. Why do we not write a Ka for a strong acid? The number wouldn't be so strong. Not quite. Right, just because the products are the same. Not quite. Anybody remember the difference when we drew out the initial reactions between a strong and a weak? I said strong acids do this, weak acids do this. There we go, Chris. Strong acids completely disassociate. We do not have the double arrow. You can only write equilibrium for weak components, okay? Because you get this double arrow, and that's where you can have an equilibrium. Because remember, equilibrium is all about the forward and the reverse rates of the reactions being the same. We don't have a reverse reaction when you have a strong acid, okay? We get complete disassociation, okay? So no reverse reaction. That's why we don't write Ka, okay? Just for weak acids. All right, questions so far on acid-base strength. I think the next thing, we're going to keep talking about Ka for a minute. Okay, so I have a whole slide just on the acid dissociation constant. So here's our reaction, and here's the K. Oh, I knew it. It's okay. I knew I was moving on too fast. Oh, one more. You bet. All right. Here we go. So I want you to know what Ka tells us and why Ka is important, okay? Because I would not bring equilibrium back up. I wouldn't do that to you unless it was actually important, okay? So Ka directly tells us about the strength of the acid. Okay, so remember back in the day when we did delta G and we were like, look, delta H and delta S are indirect ways to tell if a reaction's favorable, but delta G is a direct way. You can look at the sign on delta G and you can know if the reaction's favorable or not. Same idea here. Ka tells us directly about the strength of an acid, okay? So if you have a really big Ka or if you have a really small Ka, you'll be able to know in a minute, oh, that's a strong acid or that's a weak acid, okay? Just from looking at the value of Ka. So let's think about this. The larger Ka is, the bigger the number, the more that your products are favored, okay? If you have large number up here and a small number down here, when you divide, you're going to get a big Ka. So that means you have more products if you have a larger number on the top, because that's where we plug the concentration for the products in. Now, the product is the disassociation, right? And what do I mean? What do I mean when I say disassociation? We've written that word like 10 times today already. What does disassociation mean? Anybody know what I mean when I say that? Yes, Rachel. Okay, that's when the acid gives away its hydrogen. Okay, that's what we say, it's disassociated. So the product is the disassociation. So the larger Ka, the more disassociation. And the more the acid disassociates, the stronger it is. So what I'm trying to say is the larger Ka is, the stronger the acid. Large Ka, strong acid. Small Ka, weak acid. But what do I mean large and small? Like what kind of numbers are we talking about? Unfortunately, they are all numbers with exponents, okay? They're all numbers with exponents. So Ka is never going to be, like you're never going to see a number like 100 or 1,000. It's always going to be numbers that are smaller than 1, okay? So they're decimals. So something that's 5.6 times 10 to the minus 10, what is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 6. That's what that number is. Okay, that's how small we're talking, right? So these are all small numbers. It's just that some of them actually are bigger than others. So can anybody tell me what the largest number on this table is? What's the largest Ka value? Anybody see it? Or you could tell me which weak acid has the largest Ka value. Yeah, Kylie, right here, okay? On this table, okay, so technically H2SO4 is a strong acid, so that's why it says K is really large, but I think it just put it there so that you can then know HSO4 as relative to H2SO4. But anyways, this is the strongest weak acid on the table, okay? What's the weakest? Which value of Ka is the smallest? There's some pretty small ones. HPO4. Yeah, right here. Okay. So this one is the strongest weak acid. This one is the weakest. All right. So you could order them if you needed to. You could put them in order of strong to weak. But remember, they're all weak acids. Okay, we're just talking about relative strength of just weak acids. So anyways, what that means, the strongest weak acid right here, that one is going to disassociate the most. Not completely, but it'll disassociate the most compared to all these other weak acids on here. And if an acid is disassociating, we're going to get to pH in a little bit, but if an acid is disassociating, okay, into H plus and A minus, this right here is what makes a solution acidic. The more H plus we have, the more acidic something is, all right? That's why like HCl completely disassociates. We get a lot of H plus. That's why it's really corrosive, okay? So think about that. If I later ask you which solution, if I give you a bunch of acids, I say which solution would be the most acidic? Well, it's the one that disassociates to the largest extent. Can I scroll back up to here, or how far, Bradley? Okay. So I think we have, I'm going to work a homework problem for you guys. This is literally right off your chapter 10 homework. So if you haven't been paying attention or writing anything, grab a pencil because this is going to help you. You good, Bradley? Okay. All right, here it is. Problem 10.66. This is on your chapter 10 homework. So here's what the problem says. About 20% of the acid in a 0.1 mole, it doesn't even tell us what acid, but it just says about 20% of the acid in a 0.1 molar solution of a weak acid disassociates to form ions. So let's just write a reaction for a weak acid. HA, and we know it's going to make A minus and H plus. Some people might write it in with water. So if we write it in with water, it'd be like this. But this is the same thing, right? Because what did we say? We said H plus and H3O plus are interchangeable. Remember that? All right, there we go. So let's write our expression for, it says, first off, let's actually look at the question really quick. The first question is this: what is, and sorry, this is a little grainy and blurry, but maybe you can still read it. What is the H3O plus concentration? Or you could easily say, what is the H plus concentration? Same thing, okay? So, well, let's write the acid dissociation constant. Why? Because it's a weak acid. So if something tells you it's a weak acid, you're probably going to need Ka. All right, so let's think about this. Actually, I'm not sure that we do. I'm going to write it out real quick just in case, but we may not. We don't have a Ka to plug in, okay? But we know Ka would be A minus and H3O plus. So we'll have this here in case we need it, but I think we can actually solve this without the Ka equation. So anybody have any ideas on how we should even solve for the concentration of H3O plus? Anybody? Any ideas? We know, here's what we know. I'm going to move this down, by the way. We know that the concentration of our original weak acid right here is 0.1 molar. And we know that 20% of the acid disassociates. That's what the problem tells us. So we know that the concentration of these things, our products, are going to be identical, right? You don't get A minus without getting an H3O plus. Every time an acid disassociates, you get one A minus and you get one H3O plus. So the concentrations of these will be the same. Right? So anybody, any ideas? It says 20% of the acid disassociates. So that means 20% of 0.1 molar is going to be the concentration of these things, right? So how do we calculate 20% of 0.1 molar? We actually, we don't need Ka down here. How do we calculate that? What would we need to do? What is 20% of 0.1 molar? How would you get that? Well, 20%, you got to change it back to a decimal. So I see in the chat, yes, you're going to do 20 to change that into a decimal. I don't know why that just highlighted blue. I'm trying to get off of this. Okay. 20% divide by 100 here, and it makes it 0.2. That's the decimal. So that's 20% in decimal form. And then you're going to multiply that by 0.1. What do we get when we do that? 0.02. This is the concentration of our products, okay? And what we're looking for is the concentration of this. So the concentration is going to be 0.02. Now, if your problem gives you a slightly different percentage, like it says the weak acid disassociates 16% or 22% or whatever, you just plug in your percent for this problem, okay? So you would literally type in 2 sig figs here. So 0.02, you might have to do a 0 there, molar, okay? That's what we should get. Part B and C, I actually want to come back to, okay? We haven't talked about pH or OH concentration just yet. So we're going to finish talking about a few things, and then you should be able to answer parts B and C after we talk about water, okay? Any questions on how we just worked this problem? Not too bad, right? But it probably seemed confusing when you're reading it first. Like, what do I do? Okay. Water. Water is my favorite drink. Anybody, your favorite drink is water? I feel very adult when I say that. I know somebody, they used to not ever drink water. Like they'd be like, I don't know, the last time I had a drink of water, it's been like a week. They would only drink like juice or like sports drinks. It really worried me. Like I was very concerned about them. I was like, you need to drink water, please. So please drink water. Even if you don't like it, your body will thank you. But here's what we know about water. Water can act as both. I'm trying to write both an acid and a base. Water has multiple personalities, we could say. You know anybody like that? That could get weird. Okay, please don't share. All right, so we've drawn reactions like this multiple times, but really quick, let's rewrite water as an acid. So here, this is the base, ammonia, water is going to be the acid. What do acids do? They donate a hydrogen. So you write the products. What are we going to get? Should have these things, NH4 plus and OH minus, okay? Did I have a poll question, by the way? I think I had a poll question. I'm going to save it to the end. Yeah, I had one on weak acids. I totally forgot about it. All right, we'll save it for the end, if I remember. Okay, water is a base. So if water is in the presence of a really strong acid, now HCl is going to be the acid and water is going to act like the base. Okay, so when that happens, what do we get? We get H3O plus, because this oxygen is going to grab the hydrogen off that. The ammonia was grabbing the hydrogen off of water earlier. We'll get Cl minus, okay? So we've written reactions similar to this out before, but just reminding you, here's examples of water acting as an acid and a base. So it's definitely amphiprotic. Remember that word? But it gets even weirder. The story continues. Water can act as both an acid and a base with itself. You didn't know this about water, did you? That feels weird to say. Okay, even by itself, when no other acid or base are present to a small extent, this is what happens. Two water molecules see each other. One's going to act like the base. One will be the acid. Yep. So then what do we get? What products do we get? You should get H3O plus. What's left over from water when it gives a hydrogen away? OH minus. This happens to a small extent. It's not extensive, but it is important, okay? In all aqueous solutions. Aqueous means water is the solvent. So if water is present as the solvent, this is happening. All aqueous solutions. So all aqueous solutions carry some concentration of H3O plus and OH minus. All right. Now, I should have written a reverse arrow here because we can write a equilibrium expression particularly for water for this specific reaction and that one only. And it looks like this right here. K equals products over reactants, but because both of your reactant molecules are just water, we did water squared, because that would be like saying 2H2O instead of just two separate water molecules, so we just raised it to the power of 2. And again, what did we do earlier? What modification did we make to K to get Ka? So K for a particular acid, what did we do? We pulled water out of the equation. Remember, we said water is going to be present in a really, really high amount, so we're just going to pull it out of the equation. Same thing here. Just like Ka, we remove H2O. We're just going to take it out of the equation. And what is left over is what we call the ion product constant. Ions, because this is a cation, this is an anion, so they're two ions. What are we doing? We're multiplying them. So that's where the word product comes in. Ion product constant. This is going to be a constant value, okay? These two things are going to give you a constant value. And it's just for water, so we call it Kw instead of Ka. W for water. So Kw is equal to H3O plus times the concentration of OH minus. Okay? So we call this the ion product constant for water. You can just call it Kw. Everybody with me so far on water? So we saw that we have a reversible reaction for water. This happens in all aqueous solutions. We wrote out the value for K. We took water out of the equation, and then we said, okay, what's left is Kw. So this is the most important part of the slide right here. If you got nothing else, just get Kw. So we have Ka and Kw then. How are these different again? How are they different? Well, Ka, first off, is for weak acids only. Kw is for water only, for water. Okay. Ka is H3O plus and the conjugate base of the weak acid over the concentration of the weak acid. Kw is just the concentration of H3O plus times the concentration of OH minus. Okay. All right, you've already written these, so you don't have to rewrite them if you don't want to. But I want you to know how they're different. Don't mix them up. All right, let's keep going. The ion product constant for water sounds redundant, duh, but it's a constant, okay? At 25 degrees Celsius, there's an actual number for it. We give it a number, we give it a value, okay? So Kw is equal, it's incredibly small. Are you ready for how small it is? 1 times 10 to the minus 14. It's insanely small. That is the value of Kw, 1 times 10 to the minus 14. So if we plug the value in for Kw, what do we get? 1 times 10 to the minus 14 equals concentration of H3O plus times the concentration of OH minus. Okay, so all we did is we plugged in the value for Kw. In pure water, where you have no other chemicals, compounds, ions messing with this reaction, we know in pure water that the concentration of H3O plus and OH minus are going to be equal. Okay? One water can't disassociate, one water can't receive a hydrogen without creating one of each of these. So the concentrations here will be identical. So what are the concentrations? That's like saying this. That's like saying now that you have 1 times 10 to the minus 14 equals x squared, right? If we say these are the same, both column x. So now you guys tell me. I'm going to make this a little smaller because it doesn't look like an exponent. There we go. How would we solve for x? X is the concentration of H3O plus and OH minus in this case. What do we need to do?
Square root.
Square root. When you do that, you get 1 times 10 to the minus 7 equals x. That's going to equal the concentration of H3O plus and OH, all right, and OH minus. Okay. All right, hang with me. I know this is a lot of really small numbers. I know you're like, where are we going with this? We're going somewhere. I promise this is important. You ready? Okay, we define the concentrations. Hold on, I thought there was a slide. No, I had another slide. Yeah, I think, no, maybe we can, yeah, I guess we can do this practice problem now. Sorry, I thought, never mind. Okay, let's look at this, 2 practice problems real quick. Now that we know what Kw is, and now that we know what the concentrations of H3O plus and OH minus are in pure water, I want to ask you this question. What are the concentrations of hydrogen? So this is H plus, or remember H3O plus. It's interchangeable, same thing here. And hydroxide, what is hydroxide? Hydroxide is OH minus. What are these concentrations if we have a 0.1 molar solution of HCl? So we actually have all the tools we need to solve a question like this. HCl. Anytime I give you a problem with an acid or base, you first need to ask yourself, okay, is this a strong acid or a weak acid? What is it going to do? So what do you guys think? Is HCl strong or weak? If you're not sure, go look at that table from earlier.
Strong.
Yes, it's a strong acid, okay? So it'll completely disassociate into H plus and Cl minus. So if initially starting out, we have 0.1 molar of that and none of these things, when this is done disassociating, what are we going to have? 0 of our reactant and 0.1 molar of these things, right? Every single molecule of this will break apart. It'll disassociate. So if we start out with 0.1 molar of this is our initial concentration, this is our final concentrations. Does it not make sense to say, okay, we'll get the same concentration of our products? Did I just lose anybody? Some people look confused. If you have, only if you have a strong acid, you can say, okay, if I start with this concentration, when I'm done, all of it will have disassociated with it. So I'll have, my concentration will be 0 of that. And if I have none of that, that means I have all products. So my concentration is identical for my react or product molecules. So that answers one of the questions, right? The first question is, what's the concentration of hydrogen ions? Well, concentration of hydrogen ions, and I didn't have to do any math here just because I know it's a strong acid. It's 0.1 molar. What would the concentration of hydroxide ions be? Whoops. How could we solve for that? Anybody know? What could we use to solve for the concentration of hydroxide ions here? This is in an aqueous solution, so water is present. could we just use our equation? Could we use KW? Can we do that? We know what KW is, okay? And we know H3O plus is the same as H plus. Interchangeable. We just solved for the concentration of this. It's 0.1 molar, right? We know KW is 1 times 10 to the minus 14. So could we solve for OH minus? Could we plug in 0.1 molar and solve for it? We can. This is how you do it. We're going to use KW to solve for OH minus. That's what we're about to do. So let's plug it in. 1 times 10 to the minus 14 equals the concentration of H plus times OH minus. So I'm just going to plug in for H plus, it's 0.1 molar times whatever the concentration of OH minus is. So now we're going to divide both sides by 0.1. Cancel, cancel. So all I'm doing is I'm using KW to solve for my other ion here, OH minus. You should get 1 times 10 to the minus 13. And that's units of molarity. Anytime we convey a concentration, it's units of molarity. Okay. Are y'all okay? Make sense? So the reason why I wanted to work this problem is because right after we do all this stuff with KW and we see, you know, this equation here and we know what KW equals, we can actually put that to use and use it to solve for useful information, okay? All right, let's work one more practice problem. What would be the concentration of hydrogen ions and hydroxide ions? Same question, but this time you have a 0.1 molar solution of the NaOH. What kind of base is NaOH? Strong or weak? Hopefully you said strong. It is a strong base. So we know just like HCl, whoops, OH, it will completely disassociate, okay, into Na plus and OH minus, okay? You could write it with water as well. You could write NaOH plus water and then write your products. So if we start out with 0.1 molar NaOH, no products yet. These are our initial concentrations. Yeah, Gabby, hold on. When we finish, what will our final concentrations be? How much NaOH will we have left? This is a strong base. It's going to completely disassociate. So how much will we have left at the very end if we remeasure the concentrations?
0.
0. And you can only do this for strong components. You can't say this for weak acids or weak bases. And then we would have all products in the end. So we'd have 0.1 molar of the sodium cations and we have 0.1 molar of our hydroxide ions. Okay, makes sense? So we actually already answered one question. What is the concentration of hydroxide? It's just 0.1 molar. How do we know that? Well, we know our component is a strong base here and it completely disassociates. So the concentration of OH here is going to be equal to the initial concentration of the base. But now the question is, what is the concentration of H plus? How can we solve for this? What did we just do on the previous problem?
KW.
Let's use KW. So we know KW equals concentration of H plus or H3O plus, interchangeable, times the concentration of OH minus. We know KW is 1 times 10 to the minus 14 equals, we're looking for H plus, and we know the concentration of OH minus. Oh, I should have written 0.1, sorry. I wanted to plug the number in, is 0.1 molar. So now divide both sides by 0.1 molar. Cancel. So same number here, but even if it was a different number, would not be hard to follow. We're doing the same thing we did in the previous problem. So it's 1 times 10 to the minus 13. When you do that math, is equal to the concentration of H plus. I keep forgetting my units. Molar. Okay, so I'm just giving you examples here of how, if we know we have a strong acid or a strong base, and we know the initial concentration of that strong acid or base, then we can always calculate the concentration of these individual ions using KW, OH minus and H plus. All right. Now we're going to shift gears and we're starting, oh, sorry, Gabby, you wanted me to go back up? I don't know what slide you want me to go up to. Can you take a screenshot of it? There's a lot written on this slide. We're going to shift gears and we're going to start laying a little bit of the groundwork to understand pH. Okay, so this is kind of it for KW. I'm still going to use a concept from KW to start now talking about pH. All right. So based on this equation, pure water, what we know about pure water and the concentrations of our ions in pure water, we can start making statements about solutions and how they deviate from pure water. Okay. So a solution is considered acidic, basic, or neutral based on the concentrations of H plus and OH minus. In pure water, we know they're 1 times 10 to the minus 7. We calculated that earlier, right? If something is now acidic, it's because you have more H plus in it. So that means if the concentration of H plus is greater than 1 times 10 to the minus 7, because you have more H plus, we call that acidic. And because we know H plus and OH minus are always equal to a constant, if you have more H plus, it must mean that you have less OH minus. Okay, so the concentration of that is now less than 1 times 10 to the minus 7. So these characteristics define something that is acidic. Neutral, they are both, and OH minus. They're both equal to 1 times 10 to the minus 7. And this is units of molarity. So you guys tell me, what do y'all think I should write for a basic solution? Something that is considered basic. What kind of concentrations would you have? Opposite of acidic? Exactly. That means your H plus is now less than 1 times 10 to the minus 7. And concentration of OH minus means you have more of it. It's greater than 1 times 10 to the minus 7. All right, so we can actually remember, I'll let y'all finish writing for a second. So the last thing on this slide says, if we know the concentration of one ion, we can always find the concentration of the other using KW. If we know the concentration of H plus, we can always find the concentration of OH minus. So instead of memorizing all of this, you can just really hone in on these two statements and how they relate to things that are basic and acidic, okay? So don't worry about memorizing all of it. Just know that if you have more H plus in your solution, it's acidic. If you have less H plus in your solution, it's usually basic, okay? So there's kind of a trend here. The higher the concentration of H plus, the larger that is, the more acidic something is. And the lower your concentration of H plus, the more basic something is. All right, we're kind of winding down here. I think, what kind of poll question did I wanted to say? Let me check. I'll save it for the end. We've got like, oh, I was going to show you guys my favorite meme in just a second. Maybe it's one you've seen before. So we're almost done. I'm going to ask you this question about milk, and then I'm going to do a poll question. And then we'll see where we're at. So milk has a concentration of, for H+, the H+ concentration of milk, if you were to test that, 4.5 times 10 to the minus 7 molar. So is milk acidic, basic, or neutral? I really don't think of milk as acidic or basic, right? But it actually does have a corresponding pH. So is milk acidic, basic, or neutral? What do you guys think? Based on what we just set up here. And all my info went away. I don't know why this happens.
Acidic.
Okay. So 4.5 times 10 to the minus 7. This is greater than 1 times 10 to the minus 7, right? So because of that, the H+ concentration is greater, so it is slightly acidic. Not very acidic, but is slightly acidic. Okay? So what's the concentration of OH minus? How do we solve for it? Let's use KW. Yep. So KW equals the concentration of H+ times the concentration of OH minus. So we're just going to plug in. We know KW and we know our H+ concentration. So 1 times 10 to the minus 14, that's KW, equals, we know the concentration of H+ here is 4.5 times 10 to the minus 7 units of molarity times the concentration of OH minus. So we're going to divide both sides by 4.5 times 10 to the minus 7, cross divide. Cancels on that side. Anybody want to do this for us? 1 times 10 to the minus 14 divided by, put this in parentheses if you plug it all in at once, divided by 4.5 times 10 to the minus 7. Anybody get the answer? Somebody got it. 2.2 times 10 to the minus 8 molar. Okay. All right. I think I know how you feel right now, because it's probably a little bit of how I feel right now. This is my favorite meme, always at the end of the semester. This is my most favorite end of semester meme that I'm showing you. I feel like everybody, we start out here, right? We're going strong. If we were artists, I'm not an artist, so my horse would probably not look like this to begin with. But then we get halfway through the semester and we start really killing it, right? And then by the time we make it to finals, we're just a stick leg over here. I think my favorite part of this horse, I mean, just look at that. It's this stupid grin on this horse. I can't get over it. Why is this accurate? 100% accurate. Yes. Wait, so Abby, hold on. Assume temperature is 25. Yes. KW is that constant at 25. So unless I give you another temperature, which I won't, we will always assume it's 25. You'll have that value for KW. All right, so are you guys gonna make it? Are y'all doing okay? Give me some sort of emoji or something. Or do y'all feel like y'all are grasping what we talked about today? If you didn't, it's okay. I just want to go to sleep. When are our finals again? So not next week, Molly, but the week after. I don't know. I could pull up a calendar and look at the dates real quick. I'm going to launch a poll question as well. May 6th. Yeah. May 6th. Thank you, guys. May 6th. So one poll question here, because we're going to get into, look what we're going to get into next. pH scale. That's where we're headed next. Let me launch a poll question since we have a little time left. Weak acids. So I want to make sure you guys feel okay with weak. If I ask you, this is a very good example of a question I can ask you on a quiz, a multiple choice question on an exam. I'm going to scroll back up, so close your eyes. Okay, this table right here is where we talked about weak acids. If you had a 0.5 molar solution for each of the following weak acids, which one would be the most acidic? I'm going to erase everything I scribbled on this table. So look over the Ka values for these weak acids, and based on what we talked about earlier, which one would be the most acidic? Okay, I'll give you about 10 more seconds. Okay, I'm going to end the poll. I don't see numbers going up. Get your answers in. You've had almost 2 minutes. Okay. Share results. Okay, here's what people voted. Most people said that H3PO4, where is it? Right here, would be the most acidic. So here's I'm going to highlight. Maybe hopefully you guys can see this. I'm going to highlight the 4 we had. HF. We had HCN right here. H3PO4 and H2CO3. All right, so let's look at these values, the Ka values. So we had a 3.5 times 10 to the minus 4. And then I'm not going to rewrite all these. 4.9 times 10 to the minus 10. We have something to the minus 3 and something to the power of minus 7. Okay, so remember, the larger the Ka value is, right up here, the stronger the acid is. The larger the Ka value, the stronger the acid. Okay, and the stronger the acid is, the more it disassociates, and the more acidic the solution becomes. Okay, so you're going to pick the one with the largest Ka value. That would be the solution that is the most acidic. Since all the concentrations are the same, 0.5 molar, then you can simply look at Ka values. So this one does have the largest Ka value, H3PO4. 10 to the minus 3 is larger than 10 to the minus 4, 10 to the minus 10, and 10 to the minus 7. Okay, so this one would be the most acidic because it has the largest, that's my fridge, largest Ka value. Okay. If it was a different molarity, how would we find it? So then, Bailey, if I gave you different molarities, like you got 0.2 molar of this one, you've got 0.5 molar of this one, you would actually have to go in and calculate pH, which we've not learned quite how to do yet. Okay. So you would have to use the equation for Ka, solve for the concentration of H+, then you could use the concentration of H+, and solve for pH. I don't think anything in this class is the answer you wanted, right? Do I ever give you the answer that you wanted in this class for any of these problems? They're never as simple as you want them to be, right? Yeah. Welcome to chemistry, okay? Remember, you signed up for this class. Remember that. Okay, what else do we have time for? We're really winding down. So I don't really want to open a whole new can of worms, pH, until we have time to really talk through it. But you should have some more tools in your toolbox to work on the chapter 10 homework. So here's what I don't want you to do. Don't save it all for next Sunday night. All right. Please, while this is fresh on your mind, or while you have some time today, go look at that chapter 10 homework. And you don't have to do all the problems, just click through. And the ones that you feel like you're confident you know how to do them. It might be 5 or 6. But if you can knock off a few every day, that's going to keep you from having to do like 30 problems in one night and really freaking out about it. Okay.